Hi, I just wanted to go over homework 5 with you guys really quickly. So all I'm going to do is I'm just going to kind of go over the homework answers that I've posted. I think the biggest consistent problem you guys are having is you guys don't know what the normal force is. The normal force by definition is the force of the surface acting up against the object that's on it. And it's always perpendicular to the surface, and that's why it is called the normal force, because normal means perpendicular. For a box that's just sitting on the table, the box is in equilibrium, so all the forces on that box add up to 0. And in this case, the only two forces would be the weight of the box pushing down on the table and the table pushing back up on the box. So I drew both my forces about the same length. They're equal to each other, which means they're both equal to mass times gravity. And in this case, they're both equal to 196 newtons. In number 2, we're going to push the box to the side with an applied force. So some of you guys said that the normal force was the applied force. The normal force is still the force that's balancing the weight in this problem. So the normal force is still the force of the surface acting up on the box. And it is equal and opposite to the weight, and therefore it is 196 newtons. When I apply the net force equation, the only force that's acting on it to make it move is the applied force of 20 newtons. So the total force is equal to the mass times acceleration. The FA is equal to MA, and so A is equal to 20 newtons divided by 20 kilograms, which gives you an acceleration of 1 meter per second squared. When you pull a box with a rope, it's a little bit different, because you're lifting up on the box, which reduces the amount of force that the surface has to push on the box with to balance the weight. In fact, it reduces it by the y component of the tension that you're lifting with. So, in terms of what's going on in the y direction, all of the forces are adding up to 0. So the forces that are acting on this box are the tension, the normal force, and the weight. But it's also important for you to sketch in the x component of the tension and the y component of the tension. When you pull a force at an angle, you're pulling it to the right and you're lifting up on the box with Ty. So in the y direction, there are 3 forces. There's a Fn, which is the surface pushing on the box. There's Ty, you lifting up on the box. And both of those are balancing out the weight. So Fn plus Ty has to be equal to Fg. Well, Ty is just the y component of the tension, which is just T times the sine of 30, or 10 newtons. So the normal force would be 196 newtons minus the 10 newtons, which gives you 186 newtons. The box is also being pulled to the right. And the force that's actually pulling it to the right is not the tension, but Tx. So Tx is T cosine theta, or 17 newtons. And I did forget to calculate the acceleration here. The force that's causing the 20 kilogram box to move is a 17 newtons. So the acceleration would be 17 divided by 20, which would be 8.5 meters per second. When you're on an inclined plane, things are turned around a little bit. The weight Fg is always perpendicular to the floor, but because it's perpendicular to the floor, it has a component along the incline, Fgx, and pushing down into the incline, Fgy. So that the normal force is not balancing out the weight, it's balancing out Fgy. So the normal force is equal to Fgy, and in your notes and in your book, the formula is given as Fg cosine theta for Fgy. So that would be 196 times the cosine of 30, which is 170 newtons. So the normal force on this box, on the incline, is only 170 newtons. Fgx is the part of the weight that's causing it to slide down the incline, and it's going to be equal to 196 times the sine of the angle, which is 98 newtons. If I want to know the acceleration, I always start out with Newton's second law. The net force in the x direction causes the mass to accelerate in the x direction. So Fgx equals max, and ax is equal to 98 divided by 20, which is 4.9 meters per second squared. When we are dealing with things that are hanging, we're now going to turn away from the normal force. There is no normal force when there's no surface pushing up on you. But if you're hanging, there has to be something pulling up on you, and that's the tension in the rope. So the two forces on a mass just hanging is a tension and weight. They should be equal and opposite, otherwise the mass would be falling or would be moving upwards. So all the forces add up to 0 on this. That means that the tension has to have the same magnitude as the weight, 2,000 times 9.8 or 19,600 newtons. When we start accelerating upwards, now we have to define a positive and a negative direction. A positive direction would be the direction of acceleration, which is up. And, when we have a one mass system, we're just going to use our convention that up is positive and down is negative. So the tension is a positive vector and the force of weight is a negative vector. And if you're accelerating upward, you're going to plug it in as a positive acceleration. So once again, think about this. If you're accelerating upward, your tension cannot be equal to your weight because you're getting faster in the upward direction. Tension has to be winning the tug of war. It has to be a bigger number. So the way we start out with this is we go with the net force that causes it to accelerate in the y direction. The net force is the sum, the vector sum of tension and weight, which would be tension plus a negative weight, or tension minus weight. And that's going to be equal to whatever the mass is times whatever the acceleration is. So tension minus 19,600 newtons equals 2,000 times positive 2 meters per second squared because it's going up. So the tension is 23,600 newtons. And this means that 23,600 newtons is bigger than the weight. And of course it would accelerate upward. It's winning the tug of war. But if it were accelerating downward, you still use the same net force equation. But instead of plugging in positive 2, you're going to plug in a negative 2. Which means that when you come over and you do the solving, you're really going to be subtracting off to 4,000 from the weight, which is 15,600 newtons. That makes sense. If the tension is less than the weight, then it would accelerate downwards. Now, it's a little more complicated when we have more than one mass in a system. And there's a couple of different ways to look at this. The first way we're going to look at this is to look at each mass by itself. And then we're going to look at the whole system. So to draw the diagrams, we still have the same diagrams. If I look at the 200 kilogram mass, it has tension and it has its weight acting on it. And if I look at the 500 kilogram mass, it has tension and it has its weight acting on it. So I'm looking at them separately, but now let's look at the whole system. What's really going on? The heavier mass is going to pull down on the lighter mass. Lighter mass is going to slow it down. So it's going to accelerate, but it's going to accelerate in the direction of the 500 kilogram mass. So here's the trick. Whenever you have two masses, we're going to say the acceleration is positive in whatever direction the individual mass is accelerating. So for the 200 kilogram mass, it's going to accelerate up. Any vector in the up direction is a positive value. And for the 500 kilogram mass, any vector in the down direction is a positive value. But when we think about the whole system and we want to figure out what the acceleration is of the whole system, so we have two forces that are actually interacting with each other. We have the downward weight of Fg2, which is causing it to rotate around, but Fg1 is acting in a negative direction, slowing it down. So those are our two forces in question. What about the tensions? Well, the tensions are equal and opposite. On this side, the tension is negative, but on the left-hand side is positive. So if you add those together and they're the same magnitude, then they're going to cancel out. So the only two forces that are acting on the total mass are the weight of the second block minus the weight of the first block. And that is equal to the total mass times acceleration. So if I just do this algebraically, I can come up with a neat little formula. m2g minus m1g equals m1 plus m2 times a. Pull out the g on the left-hand side, and I get g times m2 minus m1 equals m1 plus m2 times a. And if I rearrange this, a is equal to the ratio of m2 minus m1 all over m1 plus m2 times g. So when you guys did your Atwood lab, you should have seen that the difference in the masses was directly proportional to the acceleration, and the total mass was indirectly proportional to the acceleration. In this case, the acceleration would be 4.2 meters per second squared. Well, what about a modified Atwood machine where we just have a mass on the table and a mass hanging over a pulley? Well, it's going to work in a similar way, but the problem is that the only two forces that are acting on the 200 kilogram block now are the normal force and the weight. There is no friction in this system. So because there's no friction, there's no force to slow down the system. Unlike in the problem above, we had F1G wasn't being counteracted by anything. It is being counteracted by the normal force. And remember that forces have to act in the same direction of acceleration, same plane of acceleration. So this force Fg1 is perpendicular to the motion of block 1, and so it's not going to affect the tension here, right? It's a little counterintuitive because in real life we know that if this is really heavy, it does because of the friction that it exerts. And we'll deal with friction in the next week. So Fn is balancing out G1, so they're just equal to each other. And we don't have to worry about them affecting the motion of the system because these are canceling, this normal force cancels out the weight force. So we also have tension acting on this. I forgot to draw that in. I apologize. There should be tension acting right here, right? There should be a tension vector. And that tension vector is being canceled out by the tension vector on the hanging mass. So the only force that's actually causing this to move is Fg2. There's nothing that is slowing it down. If there were friction acting this way along the rope in the opposite direction, then it would slow it down. So the net force causes the mass total to accelerate. Notice I'm always starting with a net force equation. So m2g equals m1 plus m2 times a, and a is equal to m2g all over m1 plus m2. And if I plug that in, I get 7 meters per second squared. So I think the biggest problem you guys are having is drawing the diagrams. Drawing the diagrams is really important for setting up the problems. And if you can't draw the diagrams, then you're going to be in trouble. And if you're taking an NCAT or any test that's a placement into one of the biomedical field or chemical field, fields that you're going into, you're going to need to know how to draw these diagrams. So it's really important for you to watch the videos that I've posted and to ask me questions. And I will be having our meeting on Thursday night, and at that meeting we'll practice doing this because I really want you guys to be able to draw those vector diagrams and apply Newton's second law in appropriate ways.